All right, so last two classes actually, we have worked in different numeration systems. Can somebody tell me the different numeration systems we've worked in? Name one. Egyptian. What else? Chinese and Roman numerals. And interestingly enough, I've been having a Roman numeral discussion with my daughter because she's reading a book, and they've got the chapter numbers with Roman numerals. And so even this morning she says, Mama, I'm on XIX. What number is that? 19. She was on chapter 19 of this book. Okay, so this is, new Roman numerals occur still today within those contexts. We're going to work at two more numeration systems today. We're going to work with Babylonians and Mayans. And I'm going to warn you that these are a little bit trickier to work with, okay? And that's why your calculator is going to be more useful and more needed today. Babylonians and Mayans, though, the nice thing about their systems is that they have very few symbols, and their symbols are really easy to draw. So those are both really good things from my perspective. So we're going to start with the Babylonians. Our Babylonians have two symbols. The values of their symbols are 1 and 10. And their symbol for the number 1 is an upside down, well, we would call it upside down usually, a triangle. Okay? And their symbol for the value 10 looks kind of like a less than sign. And if you want to leave it like that, I'm okay with that. But the symbol actually looks more like it's filled in here. Okay? Now, you need to be a little careful when you draw these because if you get sloppy, your 1s and your 10s start to look alike. Please don't make me have to guess if it's a 1 or a 10 because if I have to guess, I'm not going to be happy and you probably aren't going to be happy with whatever grade it is because you probably meant the right thing. I just can't tell. So do something so that you very clearly identify whether you're working with 1 or 10. Okay? Now, however, this is not like with the Egyptians. I'm not going to write the number, 597 by writing 50 tens or something like that. This is not good, right? They do something different, okay? So this is our first situation where we've seen doing something like this. They do some repetition of values. So they repeat the symbols. For values less than 60. So the most cumbersome, that is the longest, symbol for you to write in their system is the number 59. So if you were writing 59, you would in fact write 5 of these sort of less than signs, and then you would write 9 triangles. Okay, so it can be, cumbersome as it being really long, okay? But once you get past 60, we've got a positional base system. So this is base 60. So it's a positional base 60 system. So in our system, we have a positional base system. Our first digit, when we write down a number on the far right over here, has a value of 1, right? And our next place value system is called the what's place? The tens place. And then we have the 100s. And where does the 100 come from? Do you know why it's 100? It's because it's 10 times 10. And that's where it's coming from. And then we get 1,000, and 1,000 is 10 times 10 times 10. It multiplies by itself 3 times, and we get 10,000 after that, and that's 4 tens multiplied. So it's a positional base 10 number system. We use powers of tens. Okay? Theirs is a base 60 number system, which means they use powers of 60. That's what they do. And they do it the same way we do. They've got the smallest value on the right, and it moves over with the larger values to the left. All right, so very much like ours, they have maybe the 1s place over here. This is the 60s place right here. This is the 60 squareds place right here. We can continue to the left as far as we need to get bigger and bigger numbers. Okay, conceptually, are you with me? Like our system, but we got 60s and we've got different looking symbols. Okay? All right, one more sort of feature to make you aware of is there's some problems inherent with their system. One of the problems is that they lack a 0. They don't have a 0. And you might think, okay, but none of the systems we've talked about so far had one. Now the Chinese did, okay? But the Romans didn't, and it didn't cause them any problems. The Egyptians didn't, and it didn't cause them any problems. And I agree with you, it didn't, but remember, they didn't have a positional system. They didn't have a system that was worth 1's place and a system that was worth a 10's place and so forth. So this lack of a 0 is going to very quickly cause us some problems. And the numerals are, because of this, the numerals are subject to misinterpretation. All right, so we're going to do some symbols. The first one is we're going to take their symbols and turn them into ours. All right, so I don't think these are on your sheet, are they? So go ahead and write in numbers 1 and 2. We have 2 less than signs and then triangle, 2 less than signs and 2 triangles for number 1, and then number 2 has the same sort of pattern. Write those down, and then we'll talk about how we work with their system. Yes, they're stacked. Because they got that stacking thing going on like the Egyptians did.
So there's 2 sides of the 2 triangles are on one, and then the bottom is...
Say that again, Nicole.
Like the 2 less thans and then the 2 triangles on the top. Is that the top row, and then all the others are on the bottom?
Yeah, no, it moves from left to right. So this one right here is one number, and this is one number, and then this is a value, and this is moving left to right. It just doesn't get, yeah. No, it's not like one row and then we go to the next row.
Okay.
No. Can I start the first? Okay, so the first thing you need to know is how to break them apart into place value. Okay? So do you remember when we worked with the Roman numerals? And with the exception of their weird subtraction cases, it was always the bigger numeral before the smaller one, right? Same thing's true for the Egyptian or for the Babylonians. Okay, bigger numeral before the smaller one. So when you see this right here, you see the bigger numeral. Okay, so let's move from the right side to the left side. The right side, I've got the triangles, which is my values of 1, right? And then after my triangles, as I move left, I see that I've got the less than signs. And then again, moving continually to the left, I've got less than signs and triangles are smaller in value. Agreed? So the natural break right here is here, because I wouldn't have a smaller value before a bigger one. So I actually have 2 place values. I have 1 place value that is 2 triangles, and 2 less than signs and a triangle, and then I've got the second place value that's 2 triangles to 2 less than signs. Is everybody with me? Do you understand how I made the decision if we're to break this? No. Who said no? Mark. Okay. So what we want to remember, and you can write this down too as you're working, this is 10 and this is 1. And I wouldn't have within the same place value the number 1 before the number 10. I would always have a bigger digit before a smaller one. So for instance, when you see this one here, that's perfectly fine because the 10's coming before the 1. So the 2 10s and then the 1s all get grouped together because it's bigger value, smaller value. But I have to do the, what's that? Yes, within the place value. Yes. So the first set of, the second set on the left, on the right-hand side, this second set of blue right here is 1 place value because I have big, small. And then it breaks when I move to the left because I've got another small digit in there. Does everybody see that?
So how do you read this?
We're about to do that. Okay? So let's start on the right-hand side with the blue that's underlined. I have 2 less than signs. They're each worth 10. And I have 2 triangles. They're each worth 1. So think in terms of just an additive approach. What number would that be?
22.
That's 22. Now, that's not it. I'm not done, but I'm going to deal with that 22 in a moment. Now, what about the number in front of my blue vertical bar?
21.
That's 21. Now, this is not 21 plus 22. It's not 2,122. It's nothing like that. I've got a base 60 system. This place value is worth 1, and this place value is worth 60. And if I had a third one, which I will in the next case, it'd be worth 60 squared and so forth. Okay? Each of their place values are not worth base 10. It's not our number system. They're worth 60s. So the way that we approach this is we actually multiply. It's like saying, I came into the room and I gave out bags of crayons. Okay? It's very exciting, and you would all start coloring. So bags of crayons, and I gave out 21 bags of crayons that had 60 in each bag. Could you tell me how many crayons there are? Sure. What would you have to do? Multiply. You would multiply 21 times 60. Because 21 of you in the class were super lucky, and you got a bag with 60 crayons in it. Okay? But we got more than 21 people in the class, so not all of you did. I came in the classroom also, and I just had some loose crayons in a box. I had 22 of them. So the rest of you had to come up and just get a few crayons from my box that had 22 leftovers. Okay, so 21 bags of size 60, and then 22 leftovers, and we could figure out how many bags of, or how many crayons individually I brought into the classroom with multiplication and addition. And that's what you need your calculator for. So I mentioned it before some of you came in. Today and today only, if you don't have a calculator, I'll let you use your phone. Okay? As a calculator, not as anything else. So grab your phone out if you need it. Somebody multiply for me 21 times 60 and then add 22. What do you get?
1282.
What is it?
1282.
1282. So this Babylonian numeral is worth the same value as our numeral 1282 is worth. Are you with me? Okay. We're going to do it again. We're going to divide them up again. So we're going to start moving, problem number 2, from right to left. So here's a value of 1, and this one's a value of 10, and this one's a value of 1, which means I need a blue line right here. I've drawn it. It'll show up here in just a second. There we go. Make sense? Okay, I've got a triangle worth 1, I've got 2 less than signs worth 10, and then after my less than signs moving again, I've got 3 triangles worth 1. So I've got another blue line right here. And then I've got 3 triangles here, and I've got 4 less than signs here, which is perfectly legit, right? It's weird, isn't it, Mark? Yeah.
So a triangle just can't come before a less than sign?
Not within the same place value, yes. That would indicate a place value change if it happened, which is what we're identifying to start with, right? Okay, so I've got 3 place values here, correct? So this would be like a 3-digit number in our system. This is a 3-digit number, okay? Now, let's identify what the values are in each of the places. Starting on the far right-hand side, triangle and less than sign is what number? 11. In the middle, 2 less than signs and a triangle is worth 21. And on the far right-hand side or far left-hand side, 4 less than signs and 3 triangles is worth 43. But again, I don't add those 3 digits together, 3 numbers together. I don't just stick them together. They all have to be related to base 60. Okay? So this is my ones place. This is my 60s place, and I'm not writing this as though it's fractional either. This is not a fraction I'm writing. And this 43 is in the 60 squared place. What is 60 squared? 3,600. It is. So now you can imagine I come to class and I bring in 43 bags of crayons, and each bag of 43, each of those 43 bags has 3,600 crayons in it. That's a huge number. It's a very huge number. And then I also bring in 21 bags of size 60 and 11 bags that are 11 individual crayons just left over. Okay? The process is still the same as first part. I multiply the place value by the number that's in that place value. So I'm going to multiply 43 times 3,600. And then I'm going to add that to 21 times 60. And I'm going to add that to my 11 that are left over. Now you know why you need your calculator, right? Need's not the right word. Now you know why your calculator's handy. So you can do all of this stuff, but it's handy. What do you get when you take 43 times 3,600 plus 21 times 60 plus 11? Yes, it is. Everybody's coming up with the right answer. That's good. So this is how they would write the number 156,071. This is their expression of what's equivalent to that value for us. Okay? But we don't just want to take their digits and turn them into ours. We also want to take our digits and turn them into theirs, which is our next slide. Okay? This process is a little bit trickier. Okay? So anytime, and you can write this down on your paper, in fact, please do, anytime you take their system into ours, it's a multiplication procedure. Their numbers into ours, we used multiplication, and we had some addition, of course, there too, but it's multiplication. What do you think it might be if we go the other direction? It is division. And the thing is, you need to know what you're dividing. So you're always going to be dividing by their place values. So we've already established what the first three are. They've got a ones place, a 60s place, and then what? 60 squared, which was 3,600. And could we go again? Sure. We'd have 60 cubed, and I think that's like 720,000 or something like that. We'd have a larger number. Okay? So, but we have 1, then 60, and then 3,600. That's what we want to, that's what we want to remember. Okay, 160, 3,600. You can hardly read that up in the corner, but write it on yours so that you can. Now, I'm going to show you something that your book does not show you. I'm teaching out of another book that encounters the same material this semester, and I love what they do next. So I'm going to show it to you. Okay? We're going to do division, like you guys established with me just a moment ago. And the first number that we're going to do is we're going to divide this number, 3280, and we're going to divide it by the biggest one of those digits that'll still go in. So will 3,600 work? No.
Okay.
Thanks, Mark. 3280. Can I divide that by 3,600 evenly? No, it won't go in. It's too big, right? So the biggest value of that 160, 3,600 that will go into 3280 is 60. So I'm going to choose to divide by 60. Okay? And you're going to grab your calculator. Your calculator is going to tell you 3280 divided by 60, and you're going to tell me what the whole number is first. What whole number of 60s go into 3280? 54? All right. 54. All right, so we've got 54, and then we're going to take, this is long division, like from grade school. You're going to take 54 times 60, and what is 54 times 60?
3240.
3240. And I'm going to write 3240 down underneath the 3280, and I'm going to subtract. And I'm going to get, what is it? 40. Okay? And now we're going to take the next place value. Well, the next place value is 1. That's all I'm left with, right? 60 and then 1. And how many times will 1 go into 40?
Wait, how did you get a 40?
We subtracted. This is just division.
Oh, okay.
Long division with subtraction involved. Yeah, somebody told me it'd go in 40 times. And of course, 40 times 1 is 40, so we get no remainder, which is our goal in the end. Okay, so we have 54 and we have 40. So I'm going to go back a slide for a moment, okay? So the 54 and the 40, that's these numbers right here that I just got. Okay? I got 54 in the 60 place, because that's what I got when I divided by 60. And I got 40 in the ones place, because that's what I got when I divided by 1. Okay? I'm not 100% sure you guys are with me, but let's see what happens next anyway. Okay, I need to move this because I'm running out of space. So I'm going to go over here with it. I need to write 54. How do I write 54? 5 less thans, 4 triangles, and you can either write the 4 triangles on top of each other, you know, 2s and 3s, or you can write them. I'm not writing very good triangles on my smartboard today, or my iPad today. So there's 50. I didn't write 54. Hang on. Let's try that again. 5, 1, 2, 3, 4, and 5, and then 4. That's 54, correct?
Yes.
And then how do I write 40?
4
4 less thans. Either stack them or don't. And then you're done. That's your answer. Okay, so it was about division, and then it's taking the values you got from the division, 54 and 40, and writing the digits they correspond to with their numerals. Okay, but 43,205 is a bigger number. And when I'm doing that number, 43,205, I can actually take the 3,600 and it will go in. And I'm pretty sure if we go up one higher, it won't. Somebody tell me what's 60 cubed. 216,000, which is too many, right? Because I only have 43,000 here. So 3,600 is the right number. So you're going to take your calculator and you're going to divide 43,205 divided by 3,600. And I want to know the whole number part. I know there's going to be decimals. What'd you get? 12. All right. And then take your calculator and you multiply. Okay, so in long division, typically we would have written the 12 on top here. Right? If you were doing this back in elementary school, you would have 12 on top here, and then you do 12 times 3,600. So 12 times 3,600 is 43,200. Okay, subtract. What do you get? 5. Isn't that nice? Well, you need to be a little bit careful, and I'm going to make you be a little bit careful even right now, because you're going to need it when we get to 4.4, section 4.4. Very technically, we should be looking at the next place value, which is 60. Does 60 go into 5? No. So this will go in 0 times. I multiply 0 times 60, and I get 0, and I subtract, and I get 5. Now, I know that seems sort of silly, but you'll very much appreciate this later on, okay? So don't miss any of the place values. The next place value, though, is the number 1. All right, so how many times does 1 go into 5? 5 times. 5 times 1 is 5, and then I get a remainder of 0. Once I get a remainder of 0, that is the point when I'm done. Okay, I got to move this over so I've got some space. These values right here, 12, 0, and 5, are the ones that I need to write numerals for now. How do I get the number 12? Less than 2 triangles. How do I get the number 0? I don't have anything for the number 0, which seems to cause me a problem here in a moment. How do I get the number 5 at the end? 5 triangles. It's an awesome question, Tiangela. When I've got the number 5, it does okay because I've got this going on, right? So I can stack the 5. So that helps me a little bit, but it still doesn't help me with the problem of the 0, does it? Because if we started with this right here, you probably would not come up with the value 43,205. What would you probably come up with? You would have broken it apart here. You may have come up with 17 if you hadn't broken it at all, especially if I didn't stack these, right? You may have looked and said, oh, I can count those, and there are 7 of them, and I've got a 10, so this is 17. So this could be 17, right? This is very similar to how we could have written 17. If you notice the stacking as it's drawn, you might have broken it right here. And then you would have had 12 times 60, right? That would have been a legitimate thing to do. You would have said, oh, this is 12 and this is the 60th place, and then I'm going to add 5 to it. What is 12 times 60 plus 5?
725.
What is it?
725.
725. I'm going to take your word for it. So, unfortunately, the number 725 would look exactly like the number 43,205. And depending on if we stack things or not, it'd look an awful lot like 17. And I don't know about you, but if somebody owed me $725 or 43,205, I want to make sure I get the right amount of money from them. This seems a little bit problematic, doesn't it? Yeah, it is.
Too much of a loan shark to be doing that.
What's that? A loan shark. All right, so this is inherently a problem within their system. All right, so you don't have to worry when you're writing the digits, just writing it the way that we just did, or even if you don't stack them, it's fine. We're all aware that there's a problem with their system, and we're not here to try and fix it, right? It doesn't exist today, so it's been fixed. Yeah, this is the answer right there.
We just separated it.
There's a reason. I would think that they probably did, but they didn't fix it. They, as far as I know, well, eventually they're no longer using this system, right? Right. They're not around anymore. All right, so we've got the Mayans next. Okay, moving on to Mayans, all right? The Mayans. The Mayans are known for lots of things in the mathematical world. One of the things they're known for, though, is that something important. This year. Why are they known for this year?
I'll let you explain that.
All right, so did you know that the world is coming to an end? It is. We already passed it. It was June or something, wasn't it? But just in case they were off by just a little bit, you better make sure that you and God have this thing going on. Because if the world ends, I want to make sure I'm going to the right place. I don't know about you. All right, so the Mayans are known for lots of things. But let me talk about their number system. They have 3 symbols, okay? They've got the value 0. So, hey, that's good. They've got a 0. They've got a value for the number 1. And they got a value for the number 5. Okay? Those are their 3 symbols. Okay, are you guys with me? We're still talking about the Mayans and the world ending? Okay. All right, so their value for the number 0, I'm not a good artist, but it looks sort of like a clamshell. So imagine that that's what that looks like. Their value for the number 1 is a dot, and their value for the number 5 is a line. Simple, very simple to draw. The clamshell's the worst one, and you don't encounter it all that often. So they're one step above the Babylonians anyway, because they've at least got the number 0, and that's a good thing. All right, they got other problems we'll talk about, but they do have a number 0. All right, so the first issue is that they also have something going on that we've seen back in the last section. They write it vertically. Okay, so this is written vertically like the Chinese. And also, just like the Chinese, the lowest place values at the bottom, the lowest values on bottom, okay? They actually have what's called a modified base 20 system. Okay, so base 20 system would mean like our base 10 system. We have the ones place, and then we have the 20s place, and then we have 20 squared and 20 cubed and 20 to the 4th and so forth, right? That would be a base 20 system. They don't exactly have a base 20 system. It was modified. You saw that word, right? Modified. Okay, so here's the kicker. I'm going to write it vertically because they do as well. They've got a place value that's for 1. And then they've got a place value here. These are just lines to represent placeholders. I'm not trying to represent their 5-digit, okay? This is not what I'm doing. I'm just trying to show where they're showing it's going up. They've got the 20s place. The next place they have is 20 times 18. What is 20 times 18? Tyler's getting it for us. 360. Any guesses as to why they liked 360? 360 days a year, and that is exactly what they used it for. Yes. Okay, now there's not 360 days a year, but it's close, very close to correct, right? That's what they were using it for. Do you know another 360? Somebody was about to say it. A circle, the degrees in a circle. This is a very related idea, right? And then after this one right here, then they do powers of 20. So now we've got 20 squared times 18, 20 cubed times 18, and so forth. So all the powers of 20 continue after the second place, right here, third place from the bottom up, or I've got 20 times 18. I don't have 20 squared here. I've got 20 times 18, and then I've got powers of 20 after that. Now, if it helps you, because you get to use a note card when we take our test, right? Write down what those numbers are so you don't have to remember this is a modified weird base 20 system thing going on. We already decided that this is 360 for 20 times 18. What's 20 squared times 18? 7,200. My numbers are all running into each other. And then 20 cubed times 18? 144,000, which is an also interesting number from Bible stuff, right? It is. All right, I can't get my 0 in there because it keeps moving my screen. Let's pretend like there's zeros at the end. That's 144,000, just kind of written on an angle because my screen keeps changing. Okay. 7,200, yes. And then I've got 144,000. Hey, look at that. You can't read it, but it's all there. That's not my goal. All right, number 3, the third issue, or the third feature that we want to talk about, is that they do repeated symbols within a place value. That's what the Babylonians did too, right? They repeated some symbols within place value of 1 or the place value of 60 or so forth. Okay. I am going to convert one of their numbers and then we're going to stop for today because I want you to have a chance to practice and we'll just pick up the rest of theirs next time. All right, we're going to do number 5. The first thing I need to show you is how they write their numbers, okay? So you see some lines and some dots, and just like with the Babylonians, we had to decide where does one place value end and the other one start. Well, in their system, they always put the lines under the dots. So if you ever move from dots to line, that changed your place value. So the place value changes right there. The dots and the lines below are in one place value. The dots and lines above are the other place value because this just has 2 spots. So I have sort of like these together.
So the dots divide it, you said?
Going from dots to lines divide it. So if you would never have a bigger value on top of a smaller one in their system. So you would not have a line on top of dots within a single place value.
Okay, so the first place value is line, and then the dots.
The first place value is the top one. Let's talk about the top. The top one has 4 dots and 1 line. And then the next place value under that, okay, would be what do I have? 4 dots and 2 lines. Okay, so lines are worth 5, dots are worth 1. Starting at the top, what number is that? That's 9. Right? 4 dots, 1 line, 5 plus 4. Below that, I have 4 dots, 2 lines, which is the number 14. Again, please do not tell me this is the number 914. It's not what I have going on, okay? Because I have place values here. This is the place value of 1, and this is the place value that's worth 20. So this is me walking in and having 9 bags with 20 crayons in each bag. And then having 14 stray crayons in some box. Okay? So I do the same thing I did with the Babylonians. What operation am I going to be using? Multiplication. I take their number into mine and I use multiplication. So I have 9 times 20 plus, and then I have 14, or 14 times 1 if you prefer to think that way. What is 9 times 20? 180 plus 14, 194. So our equivalent numeral is the number 194 to this symbol distribution in their system. Are we good? Okay. I'm going to pause there because I want to make sure you guys have some time.